Hello, I'm Mark from Anastasia Labs, and let me give you an update on the smart contract formal verification framework Catalyst project. We won this in Fund 12, and after a rocky start, we finally got to the end of milestone 1, which is basically the COQ implementation of the COQ machine implementation in COQ. The repository is public and available under Anastasia Labs, and it's named COQ-UPLC. In the implementation, we opted to use the formal specification of the Bluetooth core language, which is still in draft, the latest one version, and we went through and implemented basically almost the whole COQ machine. This is the most important part, which you can see here in the screen. This is the step function that describes state transitions inside the COQ machine, and on the left hand side we can see the implementation in COQ. We opted to follow the same mathematical notations that's used in the specification, but we also added some minor modifications to clarify each term where it's needed. So we use the U prefix for UPLC terms, to describe the UPLC terms, use the V for COQ values. These are COQ values here. On the left hand side in the implementation we actually highlighted them with the prefix V. Used F for the frames. Most of the left hand side here are the frames, and we used the F prefix to highlight them, and also we used A and the specific notation for built-in arguments to reduce confusion within the COQ interpreter. Now what this allows us is to define UPLC programs inside COQ. And as you can see, COQ is an interactive theorem prover, which means that during development we execute commands and receive the results from the interpreter. So here is we have an examples file which contains a number of proofs that we could quite easily implement. So first of all, we can define the UPLC programs with the help of the UPLC module that we implemented. So these are the UPLC terms, and this is the program prefix on it. Now, after we have a program, we can define logical statements on it, which is if we run the COQ execute programs with the program that's defined there with no arguments. Also, what we have, because COQ is deliberately non-Turing complete, each function must finish in a finite number of steps, and the number of steps are the maximum number of steps that the program allowed to take is the last argument for it. So this is basically just a large number that's chosen that guarantees termination of the COQ machine. And as we can see, the statement is that if we execute this program, which is a simple subtraction, so basically we subtract 11 from 55, and we expect the result to be, well, first of all, a successful result. The final machine state should be the halt, that's the normal termination, and the result should be the integer 44, right? And since we actually implemented the COQ program, the compute tactic is quite useful in this sense, because just by invoking it, it will calculate the final result of the last state of the machine for us, which is exactly the same as what we had, so we can finish the proof with the reflexivity. And we got a mathematical proof that this program evaluates to 44. Now the next example we have is a little bit more complex. Basically we are calculating the absolute value of the input argument, which will be called n inside the program, but the UPLC built-in functions, there doesn't exist an abstract absolute value function directly, so we need to implement it in terms of the built-in functions that are defined in UPLC, which we can use if then else, less than, and subtract. These are implemented in the library currently. So we have the program defined, and the first proof that we have is just an example, basically, that if we compute the absolute value of the integer 5, then we receive 5. Again, this number shouldn't concern us at the moment, because that's the maximum amount of steps that the COQ execution is allowed to take. And again, the compute tactic is quite helpful to us, because it showcases the last state of the machine, and hence that we can just finish the proof with reflexivity, right? And after that, the next one is a little bit more complex. So in this state, this proof, we actually prove that for all z is the notation for integer numbers in COQ. So we prove the statement for all integer values which are unbounded, that if we give that paradigm as an argument to the program, at a maximum of 37 steps, it will compute the absolute value of the given number. Now keep in mind that this z.abs is a built-in COQ function, so it's coming from the COQ standard library, which means that it is very very stable, and it should always compute the absolute value of the I integer correctly. So in the proof script, first we introduce I, so basically we put I up to the premises. Afterwards we just use the induction tactic as usual, that separates our statement to 3 separate cases based on the construction of the integer. So the integer can be a 0, the integer can be a positive value, or it can be a negative value. So these are the ways that an integer can be constructed in COQ. So as usual, we call, basically first we select the first goal, which is the case for the value 0. The statement is quite simple in this case. Compute, of course, and reflexivity does the trick. The same is true for the next goal, so we can select the next goal, which is for the positive values, and if we do the computation, you can see that the compute tactic actually computes the left hand side and also the right hand side, so it simplifies this expression, simplifies it to just the original value, right? And we can now use reflexivity again. And the last one is the most complex case, basically the negative numbers. Compute also works here. Now we have 2 other programs which are a little bit of variations based on the integer calculation. We are an integer calculation program, in a way that since UPLC execution is strict, evaluation is strict actually, the if case in this sense, so the subtracting n from the integer 0 will always be evaluated in the original program. but if we want to avoid that, so that we only evaluate that in the case if it is actually needed, for that case we can create functions. So but the difference here is that we do not return the actual values that we computed, but what we do is create functions that accept an argument that won't be used at all, and then of course at the last step we call the return function with the unit value, so that the subtraction will only happen when it is actually needed. So the same spiel we have. So we just want to have an example that for integer 5 we receive the integer 5. Of course, compute reflexivity works, and we have the same proof for the general case, that for all integer values we will get back the absolute value of the integer if we execute the program. And that's the main idea, is that proof automation and good usage of tactics, we can just very much simplify the proof scripts. And the last one, just for curious, just for some giving you some ideas, is the same program, but we, instead of functions, we use delays, and in the end we force the returning value. And for this we only have the proof. I only stated the proof that the two programs, this delay with the delays and the original one, the lazy one actually, are returning the same values for the integers. And of course our standard tactic works to prove the statement. So thank you for your time, and hope you will enjoy using COQ PLC once it's finished.